So welcome to the session on Bayesian perspectives on adaptive testing. And I was very pleased with the keynote because it perfectly laid the groundwork for what we are going to talk about. So I'll sort of summarize basically the keynote in 2 slides and then show you how everything could be very neatly and in an integrative way could be dealt with from a Bayesian perspective. So I'll be the first speaker, sort of set the scene. And then there he is, happy to see him. How Ren will continue and generalize everything to polytomous items. And then Diao will follow up with another Bayesian application and how to deal with incomplete CAT. So let me just get started. And this is what I'm going to do. I talk about continuous testing, and that's where the seamless interfaces with the keynote we just heard. Then it's taught about statistical modeling, Bayesian parameter updating, optimal design, shadow test approach, and then illustrate everything using the case of embedded item calibration. So I fully agree with the speakers we just listened to. CAT is more than just picking an item at a time and then updating the score and then reporting the final score. You're done. I think it's an instance of, I always like to step back and look at the whole thing more formally and then sort of see if there are resources that help us to resolve the picture that emerges. So here are the 4 observations, I mean, sort of a formal characterization of CAT. It's multiple sequential statistical processes. It's not just picking one item at a time, and I'll give you a couple of examples. And then each of the processes should be modeled. It's the only way to deal with them. And then they have parameters, and these parameters serve alternatively as intentional nuisance parameters. Sometimes I'm interested in this parameter, and then the next moment I'm interested in another parameter for another reason, and I'll give you examples. And then data arrives. Not just responses, but we record response times, and all the other data you want to know, you want to collect. But you also collect design information about which item is selected, which by itself is a datum, and other data. And then you update the parameters. And then at the next step, you optimize. And that's where the sequential process becomes adaptive. So rather than what we do right now, starting a test and collecting all data in huge batches, and for large-scale testing programs, these enormous data files, and then process them at once, and then have another process that starts because it needs the input from the previous, I mean, the item calibration and then scoring, etc. Everything happens now in baby steps. Each time something arrives, information about the item has been selected or the response time has been recorded, something already happens, you update. So you're up to date each time rather than wait and then update the whole thing. So here are a couple of processes. Ability estimation, of course. That's what we ultimately do a CAT for. So what's the intentional parameter here? That's the XMNE parameter. And all other parameters are just nuisances. We need to acknowledge their existence. They have an impact on what happens, but we're not interested in them as we're interested in ability. Item calibration. That's just a change of parameters. We're now interested in item parameters, and now the ability parameters and all other parameters are nuisance parameters. And there are tons of them. Each XMNE brings its own parameter. And then we might be interested in monitoring item and test security. And I'm very much in favor of doing that in a statistical approach with modeling the cheating process that has its own parameters. So now those are the intentional parameters. I want to find out what's going on. Time management. I want to find out how much time the items take while I'm testing. So those are the intentional parameters. I might be interested in reporting back to a candidate how well he is proceeding time-wise. Then the person's speed parameter is an intentional parameter, etc. Test norming. If you want to norm the test, I'm now interested in distributional parameters rather than the individual item parameters. Those are the intentional parameters, and all the other parameters are nuisance parameters. Item exposure control. Should model this, and we can model them. I'm not going to discuss that right now, but now the exposure parameters are intentional. Those are the ones I want to manage and update. Okay, I hope this is clear. So it's the picture of just being interested in the person parameter and updating, etc., that's quite incomplete. That's a point made in the keynote address we just heard. So what tools do we have? Well, first of all, models with explicit item and XMNE parameters. And I'll just give a few well-known examples there. Then we have the technique of Bayesian parameter updating. The focus shifts to a parameter I'm interesting and a piece of data arrives. I'll update that parameter using Bayes rule. And then if we plan the next step, there's another body, well-known, not that well-known in the psychometric community, but in statistics, optimal design, statistical optimal design is a well-developed discipline with tons of publications and applications to models, and all waiting to be applied to adaptive testing. But then we need to integrate everything. That was the systems approach the previous speakers talk about. And the shadow test is a unique tool to do that. Why? Well, it goes back to a field known as operational research, mixed integer programming, linear programming. And there are tons of other applications where they use these tools to manage multiple processes or multiple implications at the same time. Multiple objective decision making is a well-developed field there with all kinds of criteria and experiences and tools. So let's just import these through a shadow test approach in adaptive testing. Models. Response model, well, I'll be using the 3PL model, but show how easy it is to switch the model during this process. Response time model, I'm not going to show you an application now, but we do have applications there in adaptive testing. Probability model for item exposure control. That's a model that models the item eligibility probabilities. Alternative models for monitoring item fit and forensic analysis. Hierarchical models, cases where you not have a single adaptive test, but a battery of tests, so you have multiple ability parameters and you're interested in all of them at the same time. So it allows us to go back and forth between the various subtests in the battery. It allows also use the collateral information, etc., etc. So far for models. I'm not going to talk about any models. I want to focus on the Bayesian updating and the optimal design and the integration. My cursor has disappeared. No, this way. So Bayesian parameter updating. And that might look like a revolution. What's going on? There you go. That's nothing new. In Bayesian theory has a huge centuries of history and it has been used everywhere. From another area. But if you're interested and see how well it has worked, there's a very nice book. It's called "The Theory That Wouldn't Die" by a New York Times science writer. And the subtitle is "How Bayes' Rule Cracked the Enigma Code in World War II." Hunted down Russian submarines, and then those are just a couple of examples of where it has been used. It has been used everywhere. It's part of your spam filter. It's how your spam filter learns what spam is to you and what's not spam. As part of your any search procedure typically, or a lot of machine learning is just Bayes rule. So what is Bayes rule? Well, it's a perfect tool to use in a sequential fashion. And here's the rule. It tells me that if I have a previous posterior that summarizes the whole history so far, and a new piece of data arrives, a new datum arrives, then I can arrive at the next posterior just by multiplying the previous posterior with the probability of response over a norm and constant, which is the marginal distribution of the response. Now, this theorem has a reputation of being very time intensive. But I'm going to show you that you can updates, those Bayesian updates in the CAT context in just a handful of milliseconds using the KIP sampling. But you need a special implementation. And what's KIP sampling? KIP sampling is your cycle among the posterior distribution of all your parameters, intentional and the nuisance parameters. Every parameter has an impact on your current process. And you sample one elements from the posterior distribution given all the previous sampled elements from the other posteriors. And it's known to be very time intensive. If you try to do it in batch mode, it might take hours before you get your estimates. That's why people go to EAP or whatever, alternatives. EAP, by the way, is a Bayesian method. But here in this context, there's a very simple implementation. The only thing you have to do is save samples, small samples, 100, 200 if you want to be very critical, from your previous update in the system. So rather than saving a point estimate that has been updated, we now save a sample. That's the only change. And that allows us to implement Gibbs sample in a second, in a milliseconds. And then if you run the Gibbs sampler and you pass a nuisance parameter you're not interested in right now, you just sample the previous posterior. That's the current posterior. And if you arrive at an intentional parameter, you do a Metropolis Hastings step, which is a very simple step. Or in the fortunate case where your parameters have a conjugate prior and posterior distribution, this happens, for instance, for the log normal response time model, you do another step. But let's focus on the mental Hensel step. So, and then mental Hensel step needs a proposal density, proposal distribution, and a prior distribution. Well, the prior distribution is your current posterior distribution. It's sequential application. And what's the proposal distribution? The best proposal distribution is your current prior distribution. So let's both assume to be normal with the mean and the variance saved from the previous update. That's just the mean and the variance of the sample you have saved in the system, so that information is readily available. And then you arrive at the tangential parameter, and you need to update the posterior there. This is all you need to calculate. Remember the Bayes theorem here? We only need to calculate the numerator. The rest is not necessary. And the numerator is just the probability of the response, which is a probability of a 1 or a 0 under the 3PL model, the response you have just observed, and you use to update, and you multiply with the previous posterior. And you only have to do this for the numerator, because the denominator is what you save from your last step. And if the new numerator is bigger than the denominator, you accept the candidate value and add that to your posterior sample. And if it's smaller, you accept a new one with a probability given by this ratio, which is now smaller than 1. And if it's reacted, you just keep the current draw from your posterior information you have. Look how much simpler this is than maximum likelihood estimation, for instance. Here, the whole history is in this posterior distribution. So I multiply only with one probability. If you would go maximum likelihood, this would be a growing product of probability, 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 which is manageable if you estimate theta. But if you're now interested, if the item parameters are intentional, you might have hundreds of examinees you use, so it becomes an enormous product with all the numerical issues there. That's why we take the log, etc., and then exponentiate to go back and all the stuff. That's not necessary. The whole history is summarized in this, already summarized in this previous prior. So that's all. So the only thing you have to do is save a small posterior sample from each parameter instead of a point estimate, what every program now does. And I think I've done that too, I admit, but it's silly. I mean, I was a typical user of the EAP estimator for theta during adaptive testing. This means you calculate the posterior and then pick the average and you throw everything away. You never use it. Which is stupid. Why throw that away? Why not just keep it and calculate it in this way? And these samples allow us to get rid of any unknown parameter at any time in the appropriate way. And because we are honest about the current uncertainty about some of the parameters, all our procedures are unbiased. Bias basically is always a result of a lie. And if we just substitute a point estimate, we pretend that we know the parameter, that's a lie, and the price we pay is bias. There's another simple thing here. Format is the same if the parameters change, the parameters of interest. And if I move from a dichotomous item to a polytomous item, I only have to replace that probability there. And I just mean, in the mixed format, I could just, if I hit a polytomous item, that's probability on the polytomous model. If it's a dichotomous item, it's a probability on the dichotomous model, 3PL model. So just advantages. And there's immediate convergence. Because in the case for ability parameter estimation, the posteriors of 3K item parameters, if at the 20th item I'm updating, so I have 60 item parameters, those posteriors in the KIP sample have already converged. And there's only one posterior update parameter that's updated, the stability parameter. And the update after one response only. So I mean, it's immediate. I'll show you a few plots, immediate convergence. And David King and I have done some study here. And for instance, for the average runtime of 2500 iterations of your KIP sampler, which is way too much, 9 milliseconds to reach a convergence. And the convergence is always less than 100 iterations. Here's an example. 20 item adaptive test, real world item pool, 200 items. Calibration sample size 500, which is not big, but just, so what? We acknowledge the uncertainty, so there's no bias. And then I show you simulated examinees at 3 different values and trace plots with the first 500 iterations after 1, 5, etc. items. So the columns are for the 3 theta values. These are trace plots, so they show you how the sampler behaves. The first row is after the first item, and there's immediate convergence. So even with 1 intentional parameter and 3 unknown parameters, no issue. Of course, there's some variance, because we have only one item response. After 6 items, it's already much narrower. Well, after 26 items, it's just immediate one, it's converged, and you can use the whole sample. You have to thin there, but those are technical issues. And the middle column is, I mean, the trace plots focus centered out 0, and the other 2 nicely move to -2 and +2, exactly as you want. So this works perfectly, and is operationally feasible. So let's talk a bit about optimal design. And you know, I mean, everyone in our field likes their own item selection rule, and they have all kinds of hobbies, etc. Let's just go to statistics and pick something that's universally best and use that everywhere where we plan the next step. Optimal design theory allows us to do that. Why have all these personal hobbies? There's good statistics there. And a key quantity in statistical optimal design theory is your covariance information matrix for the intentional parameters. And we have criteria there, like d-optimality, which is the determinant of the information matrix for the intentional parameters only. So if it's an ability parameter, it's the information matrix, which is Fisher's information just for the ability parameter. It's the item parameters, the determinant of the item parameters. But we could also look at the trace of the information, the covariance matrix, or the eigenvalue, or the subset of it, etc. But the criterion of Dia's optimality is the best statistical properties. There are invariance properties and other properties in the statistical literature. So let's just pick that one and use it in a Bayesian fashion. And the Bayesian fashion is calculate the posterior expected gain of the information matrix for intentional parameters. Always. So as soon as I know what the intentional parameters, I'm ready to go and find out what the next best step is using a well-known solid criterion. The information matrix for the intentional parameters, of course, a function of the intentional parameters, but also a function of all the nuisance parameters. It's just a matter of focus. The other parameters are still there. They play a role. But you can just, in the Bayesian tradition, average them out. So you allow for the uncertainty you have by averaging them out. And that's all you have to do. And that's simple because you have a sample of all these parameters in our system. So I'm going to talk about embedded item calibration. So here are the 2 versions of the DS optimality I want to use. The one for ability estimation, which is just Fisher's information. How we calculate it? Well, we just calculated the averages over all the samples we have in the system for the parameters in the expression. So we average over Say there's a sample of capital S, 100, yeah, or so. So we take the average of Fisher's information over the 100 theta values for the candidate and the 100 theta values of the A, B, and C parameters for the items. And if we now shift our focus and interest in updating the item parameters, we need a posterior expected gain of the determinant. So it's the gain in the determinant of the information matrix. And again, we just average everything out and we're ready to go. Pick the best, take the best next step. So let's talk a bit about the shadow test approach, because we now have all these approaches and we need to integrate them. We need to do something about them in real time at each step. And there are all kinds of trades-off in the system. There's trade-offs between what's best for estimating the item parameters, what's best for exposure control, and what's best for updating the ability parameter, and what's best for time management, and what's best if you're interested in the population, dus estimating the population distribution. So you need everything in one approach, integrated in one approach. I'm not going to introduce a shadow test approach. You had your opportunity. We gave a workshop on the first morning, and if you missed that, then we hope to be back in 2 years. And if you're going to NCME, we hope to be there with a workshop. But let me just give you an example of a shadow test approach to manage adaptive testing with embedded item calibration. So we now have a double focus. We have a subset of operational items in the pool we use for the candidate, and we have a subset of field test items that are new, might have already been partially calibrated, but we want to update their parameters. And the idea is to administer the field test items at the end of the test, because then the posterior distribution of the examinee, whose response we are going to use, is maximally converged. So that's the smallest posterior distribution. But always at the last position makes yourself vulnerable. If candidates find out, they stop earlier and ignore the last, you just give random responses. So the idea is to pick a few random positions at the end of the test, say the last 3 out of the 5 items, and randomly vary across examinees. And we're going to hide the items so they don't know which of the 5 it is, even if they would know it's one of the 5. So they have to take all of them seriously. And then one of these positions is reached. In the shadow test model, we have the field test item waiting, and we just pick the field test item from the 3 items in the shadow test rather than operational item, and then continue until you meet the next position, and then you pick the best field test item rather than the operational item. And we know the criteria for item selection, and we know the criteria for the ability parameter estimates. Both are optimal design criteria. So what are the advantages? Well, much smaller samples required, because we collect all the information about the examinees first and use them in a statistically proper way if we update the item parameters. We're able to hide the field test items in a full constraint set. So it's not that if you have a test and all of a sudden there's a geometry item because you want to know more about the geometry item. No, all the constraints run across the whole shadow test, so the item is embedded in that. We can do exposure control of field test items, probably with a low maximum exposure rate, because you don't want the items already to be compromised once they're calibrated. And it's a very easy implementation. Here is what you need to do. So rather than having just a left-hand side here in the shadow test model as objective function, we now have 2 sums here. One for the operational items across the operational items, the other across all the field test items in the pool. And the shadow test tells us that we pick n0 operational items in each shadow test, and n sub f field test items in each shadow test, for instance 27 and 3. So each shadow test means you already plan the field test items you're going to administer, but the planning becomes better and better and better because you update the posterior distribution of the examinee using the operational items. And there's no compromise here. Those are in one model, 2 independent problems, because both run over different variables in your shadow test. So it's not the case that if you pick items, variables for what on the left in the first component of the objective function that I constrain the right component, the right hand side component. No, they're completely independent. So this works perfectly. Here's an example to conclude. So it's a 25 item adaptive test. Real world pool with 250 operational items and 50 field test items. 8 constraints to address the content blueprint. You could do more, but that's just up to you. 3 field test items, and we now fix the field test items because simulation has no security issue or motivational issues. You just pick them at the 21st, 23rd, and 25th position. And then we retire the field test items after 250 and 500 responses to see how well we are doing. Examinees were sampled from this distribution, and we ran the KIP sampler each time, 800 iterations with 200 for burn-in. That's too much, but just to make sure. Our recommended values are within a paper that's going to be published soon. These are the trace plots of the A parameter after 250 responses. So immediate convergence. Still some variance, but it's the A parameter, we know that. First plot a little more than in the second plot. That's also well known at a high A value, more sensitivity, less posterior certainty. These are the B parameters. That B parameter still has a high variance. I would not retire it right now. That's because it's an extremely difficult item. So that even though we have an optimal design approach, optimal sample approach, there are not many examinees that come close to a large value for your D criterion. The right-hand side is much better. C parameters. Frankly, I know I've listened to some of you here. Some of them still use the 2PL model because there are rumors out there that the C parameter doesn't work. Not in this context. I've done tons of simulations in adaptive testing. C parameter always works, especially with the Bayesian approach, especially if you have these focus samples. Never a convergence issue with a C parameter. It's a function of maximum likelihood estimation, and if you go Bayesian and do it in this context, you just use the 3PL model. The C parameter is not an issue. These are the number of items retired after 250 responses. Horizontally, the number of simulated examinees, 3,000. Vertically, the number of items that reach the stopping rule of 250 responses, and zip. So after 500 items, already 2 items retired, and then it just keeps going up. Just picks the items you want. You may not want this. If there's some items that have higher priority, you can play with priority indexing your objective function, etc. But if you just want to calibrate these 50 items and want to use them as soon as possible, after 500 examinees, the first few items already available for operational use. There's also plots with 500. I'll skip that for time's sake. You're doing better there. Oh, I'm going the wrong way, sorry. So here a couple of final comments. All other adaptive processes, speed estimation, response time item calibration, model fit checking, item security monitoring, test norming, can deal with them in exactly the same way. Each time a piece of data arrives, you update your intentional parameters for whatever you're interested in. The KIP sampler works, very simple scheme, just 10 lines of code for whatever problem you have. We always use an optimal design criterion to plan the next step. And you can manage all these processes just by constraining some of the things sometimes or combining them in an objective function, or whatever way you want to do it. But it's explicit management rather than just doing something and waiting and see what happens. If you want to know more about this, there's a chapter on this approach in the Handbook of Item Response Theory, Volume 3, that is in production right now. That tells more than I'm just telling now. And it also deals with speediness issues and time management, etc. And if you buy the 3 volumes at the same time, you get a big discount. That's it for now. And thank you.
Matthias, I will comment. Hello, everyone. Welcome to our session. This presentation will cover the topic Bayesian adaptive testing with polyatomic items. Basically, we want to extend the idea Wim just presented to extend to polyatomic items. And this work is collaborated with Seung, Choi, and Wim van der Linden. So a simple outline. A quick introduction first, then the IRG models we used, then we talk about the methodology we used for the polyatomic items, and a simulation study, and some conclusions. As we have seen so many presentations over the past 3 days, there are so many applications of CAT in the past decades or so. For example, the K212 and diagnostic and the patient report health outcomes. Along with so many CAT applications, one of the consequences is increase the pressure of the replenishment of the new item pool more frequent. We need a more large item pool, etc. So we need to develop some new methodology and calibrate new items more efficiently. But more efficient item pool replenishment may necessitate smaller calibration size. However, with smaller calibration size, calibration error of item parameters sometimes is likely to be substantial. So sometimes you can ignore, or sometimes you cannot ignore the error. In current CAT applications, incorporating the uncertainty about the item parameters into CAT for ability estimation or item selection is still not a standard practice. From the literature, maybe incorporating the uncertainty about ability estimates into item selection have been studied in a lot of studies. For example, probably use empirical Bayes method or some other global information measures. However, accounting for item calibration error both in ability estimate and item selection for CAT calls for a fully Bayesian approach. Here we give a note. Please note that a fully Bayesian approach has two counteracting effects on the standard error of ability estimates. First, since we acknowledge more errors in the whole process, so we expect increase of the standard error of ability estimates. On the other side, because we acknowledge the existing errors, so we expect a better selection of items. Ideally, we hope the later effect can compensate the former one. Recently, a Bayesian approach based on the optimized Markov chain Monte Carlo algorithm for dichotomous item was introduced in Linden and then 2015 and 2016. Because of the rapid real-time mixing of the Markov chain samples, and just use some simple calculation for the posterior distribution. So the algorithm showed it's very efficient for a dichotomous item with 3PR model. In addition, like we saw, there are several presentations talk about the polytomous items. The interest in CAT with polytomous item has grown. Unlike dichotomous item, the information function of polytomous items tends to span a wider ability range and can be multi-model, only unimodal, and in some very specific cases. So because of the different properties of model items, we expect to have consequences for the calibration size, the test length, etc. So a research objective for our study. First, we want to implement the fully Bayesian CAT algorithm with polytomous items. And we use the two models for both the generalized partial credit model and the graded response model. And we will evaluate the performance and the impact on the ability estimation. Maybe one quick go through the IRT model. First is the graded response model. The model defines the probability of selecting the ordered response categories. It's for the probability for each category is the difference between the two probabilities, and for each one is defined here. For the if the category is k is equals 0, it's 1. If it's mi is 0, and for the values between them, it just follow the 2PR model. This is the generalized partial credit model. It defines the probability of receiving a score in category K like this. And the ZI is similar, defined as a 2PR model. Now, this is the methodology we used for the ability estimate. In Linden and then 2015 and 16, a special Gibbs sampler was used. For the regular Gibbs sampler, it will iterate between among all the parameters. In this study, in the proposed algorithm, The GIP sampler will iterate between these two steps. First step, sampling the conditional posterior distribution of item parameters. And the second step, sampling the conditional posterior distribution of the theta ability parameter. In the first step, because as Wim already said, we will save the samples from the stationary part from the calibration phase. So in the CAT part, we will not update the posterior distribution of item parameters. So we will only do the random sample from the samples. So in the step 2, only one parameter left, the ability parameter. So there's an efficient implementation of metropolis testing algorithm for a single variable theta. Finally, we will save a vector of draws from the stationary part of Markov chain for theta, then use the saved samples for the later item selection. After we have the ability estimate, we will do the item selection. So first, the item selection criterion is the maximum feature information. The item with the maximum information at the current theta ability, current theta estimate will be selected and administered to the examinee. And another criterion we use is the fully Bayesian version. So now the information is the fully Bayesian version is the integral of the feature information and the posterior distribution of theta and the posterior distribution of item parameters. And this formula, we already saw it from Wim's presentation. We just plug in all the samples to the formulas, then calculate the average. In our simulation, we use the two item pools from different area. One is from the health-related quality of life measurement based on graded response model. All the items have 5 response categories, and it has high discrimination parameters, and the highest information is in the upper half of the trait distribution. Another pool is from educational testing based on generalized partial credit model. Now items have different categories, 2, 3, or 4 score points, and low to medium discrimination parameters, and the information of the pool and the ability distribution are matched with 3 test lenses and 2 item selection criteria, and we use EAP for the MI criteria and the fully Bayesian version for the fully Bayesian item selection criteria. Both, because we only have 95 items for each pool, so the test length is a little bit short. Here's the steps how we run our simulation. First, we calibrate the item pool. First we assume the item pool, the parameters are true values. Then we generate different sample size based on the true value and calibrate the pool. And then the items were calibrated using the regular MCMC algorithm. I used just another GIP sampler, not the online calibration algorithm, etc. Just to mimic the paper pencil version calibration process. Then we sample from the posterior distribution of the calibrated items, and the samples were used for CAT simulation with these 2 item selection criteria. And here the size of the MCMC samples for the fully Bayesian criteria is 1,000. It's after synced, and this size is much bigger than the necessary in the operational test. Just a more conservative choice for the research exploration. this is the results from the calibration. The top row is for the parameter A, the bottom row for parameter B, and we can see from left to right samples, different calibration sample size. We can see as the sample calibration size increased, less error produced, and calibration is more accurate. But for the smallest sample size, there are definitely a lot of variation error exists. Here is a trace plot based on a trace plot of the theta in the CAT based on calibration results of 500 sample size. We can see all the trace plots converged immediately from the beginning, and of course, here showed more variance exists after the first item, and the variance of the estimation reduced along the test length. But maybe it's because of this study is for the polytomous items, the variance is much bigger for the dichotomous one. This is the results of bias for GPCM model, and from left to right are the test lengths 5, 10, and 15, and from top to bottom are the sample size. We can see for the dotted line is for fully Bayesian version. The solid line is for maximum efficient information. The fully Bayesian version results in smaller bias in most cases. This is the standard error of ability estimate. In almost all cases, the fully Bayesian version will result in a little bit large standard error of ability estimates, especially for the shorter test length, smaller calibration size. This is the RMSE. So as we already said, we hope the two effects can compensate each other. So for the RMSE, the two criteria results similar or comparable results. This is the calibration results for the graded response model. Again, similar pattern appeared here. If we use a larger calibration size, the calibration results will be better. And for the smallest calibration size, there are definitely some variance exists. For bias, but for the graded response model, except at the extreme value parts, these two criteria results are similar results. For the standard error, again, I don't know whether you can see it clearly. There only a small difference at here. Again, for the RMSE, in most of parts they are comparable, but for here we can see there are some significant difference between these two item selection criteria. Now, this is our conclusions. First, the fully Bayesian version of CAT results in slightly lower bias, but comparable RMSEs. And differences between the two criteria reduced steadily with the increase of the calibration sample size. So probably means if there are less error exists, so there will be no difference between these two methods. But if there are some error exists, we will see the difference of these two criterions. And for the graded response model pool, the differences were generally smaller. Slightly larger SE estimates for the fully Bayesian version, and slightly large bias at extreme theta values when the sample size were small. We did some further investigation about the two models, and the difference between the two models were due to the item pool characters, not the model itself. Because the graded response model pool, it has much higher discrimination parameters. It uses a smaller RMSE, and the skewed distribution of difficulty parameters caused the different pattern at the extreme theta points. And we did some further investigation. For example, manipulated the discrimination parameter for GPCM pool and extended the test length for GPCM pool. The difference will disappear. Overall, the results from this study of fully Bayesian adaptive testing showed the practical feasibility of the implementation for CAT with the polytomous items. For efficiency, the computation time was about 0.06 seconds for both ability estimation and item selection. As I said, in this study, it's only for research exploration. We used some conservative setup. For operational use, this time definitely can be reduced even more. And this approach results in honest estimation of errors. It captures the underestimate standard error of the ability estimates, and maybe implication for the traditional CAT under the variable precision conditions. And their potential benefits of more optimal item selection, and therefore a better test design and examining experience. There potential reduction in sample sizes for calibration under the fully Bayesian framework. Even though we saw some significant calibration error exist for the smaller calibration size, because we acknowledge this kind of error in the whole CAT process. So we still can use some items with big error exist for the operational use. Yeah, that's